this is an ultrasonic flow detector. Now, ultrasonic flow detector, as the name indicated, it is actually used to detect is there any flaw in the material, especially in metal or any kind of homogeneous material. Okay, say for metal, this metal we have actually manually created this hole in here. Okay, now there's no way for us to be able to detect it unless we use this ultrasonic flow detector. Why? It is actually able to detect is there any this hole that we actually created manually or not. That is one thing. Or we use another method we call X-ray. Okay. This will be the two general method that we use for flaw detection. And this ultrasonic flow detector, we also use it to see how good is this this welding. Okay, you know, sometimes this welding may have some crack or insufficient fusion. Insufficient fusion, we call it meaning this weld hasn't really bond these two metal plate together strong enough. Okay, meaning there still leave some gaps over there, or it's not properly fused. Okay, for the welding material with the plate. All right. So how do we do it? I'm going to show you shortly. To turn on, we press this, and then this equipment come along two type of sensor. One is straight probe, the other one is angle probe. Okay, I'm going to share with you the concept how to use this straight probe. All right. Okay, first thing first, of course, we connect the sensor. This connection, you call it a BNC connection. All right, it's very easy to use and easy to connect. Now over here there's two. You only connect one at a time. Okay, one at any one time. Sorry, meaning you can for this type of probe, we can only connect one. We cannot say connect two for standby purpose. No.
Both are input, right?
Both are input.
Okay.
Unless we are using it for this two probe features. Otherwise, should we connect two probe for the normal situation, right? We will have interference. Okay, or we have a conflict in signal that we receive. Okay, so this one angle probe later. Okay, this block, I'm going to show you this block. This block is actually for calibration. Okay, this is a center block that we use for calibration purpose. The height is actually 100 mm, and then this radius is also 100 mm. All right, from this point. Okay, from this slot. Now I'm going to calibrate this meter with this straight probe. And how to do it? First thing first, of course the setting must be correct. Now first thing, we need to select the correct probe. Okay, probe type. Okay, probe type, then we will select by pressing, let me see, okay, by turning this dual or true. Okay, but for our this purpose, we are actually using PR. Okay, PR is actually for this type of setting. All right. Now, I will not be going through in detail each other function. Why? Because those function is already covered in a previous video which we have actually taken. Okay, but right now I'm just share with you the concept. Once we have selected, it is time for us to go for calibration. Okay, now we must set the range that we want to actually of course we are going to measure something 100 mm. The range that we set is actually here. This is x-axis range. So of course we could be more than 100 mm or at least 100 mm. Okay, so we put on top. Well, we are getting so many pulse. What does it mean? Okay, number one, we must check what is the velocity. The velocity for this straight probe, when we are using straight probe, this material steel is actually 5,900. So we must set to the correct setting. 5920. Okay, meter per second. Okay, now what is this? So much of you know, the amplitude is too high. We need to reduce it. Okay, so to the optimum level. okay, to the optimal level. Usually about 80% of the height for the first pulse. Okay, like this. All right. Now, and what is this? This thing we call it gate. It's actually for measurement purpose. Okay, measurement purpose. Okay, I need to press this so that it is actually by moving where is the start position. All right. So when I stop here, it's actually taking the reading here. Okay, but is it accurate now? No, it is not. It's supposed to be 100 mm. Am I right?
Yes.
Okay. What else we need to actually adjust? Let's go back to the pace. It is this probe delay. Probe delay is actually one of the functions that we use to compensate the delay of sound wave that come out from the crystal of this probe to the material. So by getting this accurate, only then we can get accurate reading. All right. Now how to do it? We press this, then we adjust. So we obtain 100. Okay, too much ready. By pressing this, after getting asterisk right, we can adjust it in a final way of adjustment. Okay, right? So like this means it is done. So we have actually calibrated this straight probe. All right, straight probe. Okay.
Yes.
Right. Now, we can actually save this setting into our actually memory if we want to. How? By pressing this memory. Okay. Now we need to select the hang on. Okay. I need to go to this channel. Now it is actually this under this channel memory that we can actually save the setting that we have just done. So like next time we turn on the equipment, we don't have to calibrate every time. Okay. Now say I select it to be stored at memory 5. Okay. Then how to do it? I just go to here, turn on yes and no. You press this enter button. Okay. This enter button.
Yes.
Save. So we have saved the memory, this setting, this setup to channel 5. The next time we want to use with this probe again, because there are various probe, straight probe and angle probe. Am I right?
Yes.
So the next time when we use a straight probe, we don't have to calibrate again. Why? We can just call up this setting that we have stored earlier. Okay, then we can use right away. All right, for accurate measurement. Okay.
It's the same with the portable one that I used yesterday.
That is thickness gauge. This is floor detector.
I see.
Two different. Floor detector is able to detect the floor.
I see. Okay.
Okay. The thickness gauge is only measuring the thickness. Only the thickness.
I see.
There's no screen display.
But that our thickness gauge that need to calibrate every time before using it.
Yes. This.
How about this one?
This, of course, better is you get one calibration block like this. Then you calibrate every time you use. But however, we can actually save. We can actually save the reading, the setup.
Okay.
We actually saving the setup already. The next time you want to use, you just call back the setup.
I see.
Two different concept.
Okay.
Can all right. Now, what is this pulse? Now, this pulse, if you have gone through, for ultrasonic testing principle, say this is a pulse, this is a material block. They will actually send out one sound pulse,
Yes.
then refracted, then this thing, what's the meaning of this pulse? It is actually here. This is the echo it actually generate. Meaning to say that this screen here, the calibration is first. This is actually initial pulse.
That sent to the material, right?
They actually come out from here. Initial pulse come out from here. Then this pulse actually transmit in the material. When it hit this back wall of this block, it will be refracted by the back wall and then go back to this crystal. All right, this crystal was sent. Then this is where it's actually send this pulse. This is actually called echo. from the back wall. Okay, so this is the echo that we actually receive. Because we do the calibration in such a way that we actually tell this unit, this pulse that you actually obtain is actually at a distance of 100 mm. Meaning, why 100 mm? Because our this standard block is 100 mm thick. So in future, when we doing the measurement or detection, right? The moment we see this pulse and then we use this gate to measure, then we know that reading is actually accurate. Why is actually accurate? Because we actually calibrate this meter according to a standard. Okay, right? Now, then what is this pulse? This is actually called wall rebound pulse. Why wall rebound pulse? It is actually generated because this wall is actually narrow. Okay, narrow. Some of the waves is actually hit the wall like this, then go back. Okay, that's the reason you are having this.
That's why you have quite a delay, right?
Yes, something like this. It has hit like this. You know, this is called interference wave. Alright, but this thing will not happen when we actually measure. Okay, this we need some coupling agent. In order for the sound wave to actually pass through. When we actually like this, then you do not see. So this will be the first echo, second echo, third, fourth, fifth. Okay, what does it mean? Hang on, okay, better contact. You may see. All right. This thickness is actually 20. I think 1 inch, 25. Hang on, Let go to gate. Okay, we remove this. Yeah, 25. Thickness of this is actually 25 mm thick. Okay, this is the first echo. This second echo, third. Okay. What's the meaning of this first and second, third and third echo? Let me show you. Now this pulse when it generated, reflected, and then sent back to this probe. It will, this pulse will actually rebound again. Second, third, fourth. You know, of course. Why the amplitude is getting lower each time?
Because of the loss.
Yes, loss of energy when it actually travel in the material. Okay, so this is a basic principle of an ultrasonic sound. Okay, travel in any material. All right. So clear on this part? Okay, excellent. Now, this part, you may see this you know, there's one teeth here. Okay. Now this is actually we use it to see how sensitive or how good is this probe. You know, how sensitive is this probe into picking up this signal. You may see here. Okay, let me adjust here. Okay, we can actually go down, move down this threshold. Okay, now this is still 100. Okay, meaning this is actually getting this pulse is actually from here. Then what about this shorter one? This is actually this. Okay, let us move. Okay, now this height here from here is actually 86 mm. Okay, then what is this? It is actually here. Of course, we will need to change the width. We need to change the width. All right, in order for us to move in and measure. Okay. So it's 92.5, meaning distance from here to here is actually 92.5. So by being able this probe to be able to show this, we say that this probe having a good definition. Okay, meaning definition in terms of getting the pulse. All right, reading in such a small gap difference. All right, so just in case, okay, not to say just in case. Okay, for example, we do not know whether or not here got flow. Am I right?
Yes.
Okay. By using this straight probe, it will do a detection. You know, by us being able to see this pulse. Hang on. Okay. Okay. Let's see what is the. Alright, I will extend the brief a little bit. Move down a little bit. Okay, this is steel and this is cast iron. So the sound wave actually a little bit different, but I just shortcut lah. I just do not want to spend more time into showing you how to do calibration again with this different material. But okay, let's see. 80 mm is actually the thickness of this. This is roughly about 80 mm, right? Okay, this compared to this is actually 100. This 80 mm. Okay, right now, how come I cannot detect this small hole? Is it so? Or it's already shown here? You can see this?
That one.
This small thing, small pulse. So only the experienced person will actually care about this small little thing. Or we can actually increase this signal. Then you can see better. Can see or not? This.
Yeah, that one.
Yeah. Okay. So by actually seeing this, meaning to say that, say this is the initial pulse. Initial pulse. This is actually echo. Okay. Any pulse that you see in between is actually something in between blocking some of the sound wave. For that reason, for sound wave that has been blocked and reflected back, it is actually a defect in there. Okay, either it is a crack or it is actually a cavity. Okay, can you understand?
Yes.
Okay, excellent. Now, any question to ask? No. Okay. Now, there's a limitation for this straight probe. What's the limitation? It cannot go to something so thin. Okay, anything 6 mm and below, it is no good for this what they call straight probe. We now change to this angle probe. All right. Now with this angle probe, right? As I said, we will need to recall the setting, because previously I have actually calibrated, and the way we record it is by pressing memory. Then we go to this channel. I remember I've actually saved the setting at the channel number 2. Okay. So in order to recall, I just turn to yes and no. Then I just press this yes. Alright, so I have actually successfully recalled the setting. So let's see. Yeah, this is a setting that are actually suitable for this probe. Okay, why I know? Because number one, material velocity is 3230 for longitudinal wave for this angle. Okay, right now you can see we now successfully getting a pulse. Alright, and what is this pulse? What is the reading? Okay, this range I've actually set to 100. Okay, as you can see now. Okay, I can actually increase the gain. Okay, now what is the reading? 100. Okay, 100. Why 100? Because this range is actually 100. Okay, from this slot. All right, 100. Now, there is actually a few settings we need to do. Number one, probe delay. We have actually, as I said, I have actually previously compensated, okay, the probe delay. Now, I need to actually look for the highest pulse, the highest amplitude. Okay, let me see here. Okay, this is the highest amplitude. Okay, this is the highest amplitude. Then I know where is the point. Okay, the point. Hang on. The probe. It's actually at the probe setting, if I'm not wrong. No, it's not at the probe setting. Let me see. Okay, at the angle probe. Okay, now for this probe, this X value, probably I need to explain what is this X value. X value is where we actually doing the calibration, whereby we going to find out where exactly is the point where the sound wave actually enter into the material. This is actually 9 mm this position. Okay, 9 mm. So this 9 mm actually in line with this slot. Okay, right? So why is so important into adjusting this? Because we have this value called P value and D value. Okay, what is P and D? D is actually the depth. Okay, the depth, and P value is actually the distance from here. The distance from here, front edge of the probe to here. So right now we can more or less saying that the sound wave is actually hit at an angle of 64 degrees Celsius. Okay, it's like this 64. Hit here. Now what is P? P is actually this distance. Okay, and depth of 81 is actually this depth. Okay, this depth. Alright. Okay, so in the past people actually need to calculate manually, but right now we can actually view from here. However, this reading can only be accurate when we actually perform the correct calibration. Okay, once we have calibrated, we can actually use it to do more more detection. Okay, now say for example, if you are actually interested to see the floor. Okay, where is the floor? Hang on. Now because this is cast iron is actually the sound wave will actually experience more losses. So we need to increase the the gain. Okay, this is gain. So this is actually the floor. Alright. So this floor means it actually can see this this floor here. Alright. So okay, see that? So if you want to know what is the distance or from this sound path, we can actually use our this gate. Okay. Now what I'm interested to show you is how they actually detect this thin thickness. This thin plate thickness. I've actually manually created one defect here. Okay, you can see a hole is actually drilled. Now, how they actually detect the floor is actually like this. Okay, I actually move like this. While I'm actually doing detection, I actually move like this. Okay, you see this? So this pulse actually showing that there's one floor here. Okay, so while people doing detection for the welding, they actually scan in this way. Okay, they scan. The moment they see any pulse like this, right, then they will actually stop. Then they will do like this, meaning a different way of scanning to see whether there got any flaw or not. Okay, so when they see this, yeah, there is a flaw. Okay, so after we have actually done a very careful calibration by moving this gate, right, by moving this gate to this position, okay, we will be able to know how far it is. Okay, where is the location? Because we know what's the distance of the depth. We know what's the distance from the probe edge. We also know the distance of the sound path. Okay, so then we more or less can know where exactly is the floor. Okay, so for any thin plate, we use angle probe. All right, for the detection purpose, especially for welding, we definitely need to use an angle probe. Okay, all right. So there are actually more function to this meter. There's this DAC. Actually, I have a very detailed video on to how to use this function. All right, this function is actually more or less like allow us to set a tolerance. Okay, a guideline. say over here, I have actually a same dimension of defect, that is a 1 mm diameter hole, set at different depth. Okay, set at different depth. Now, why I'm actually doing that? Now, DAC is actually a function allow us to set a tolerance whereby anything the amplitude more than the tolerance, we set it fail. Anything lower than the tolerance, we will probably go for a second type of evaluation. Okay, right? So that is the use of DAC function.
It's like, yeah, we set the limit already.
Yes, correct. Yes, you're right. Okay, so that's all. And the rest is actually the some of the display setting and B-scan setting. I would like you all to go to our YouTube video to have a detailed learning. All right.